All right, got some numbers here. We got a lot to go over. So I think we will get started. Welcome everyone to our Earthmover webinar on data version control with Icechunk. Just a little bit about Earthmover. We're a mission-driven startup, and our mission is to empower people to use scientific data to solve humanity's greatest challenges. Earthmover was founded by myself and Joe Hammond 2 years ago. We both come out of the climate science community and have spent the past decade working on the open source scientific Python stack, Czar, Xarray, and the Pangeo project. And so we're really excited to be building the scientific data platform of the future at Earthmover. And a big part of that is Icechunk, our new open source project that I'm going to talk to you about today. So here's the outline of the talk that I'm going to be presenting. First, we'll just give a general intro to Icechunk. What is it? I know some folks here have heard about it already, but it probably bears repeating. Then we'll talk a little bit about what is version control, why do we need version control, and what is data version control. And then I'm going to switch over to a demo where I can do some live coding and walk you through some real world examples of how we use Icechunk in the context of version control, etc. And this will get increasingly complex, and then time permitting at the end, we can look at a pretty fun real world example where we're generating some training data with a simulation and then running a neural network classifier model on that and using Icechunk to tie everything together with immutable versions. So without further ado, let's dive into it. I need to make one tweak here, sorry, to my slides, and then we will be good to go. So let's see. Okay, that problem is fixed, and now we will jump back into the webinar. Sorry. All right, so outline. Let's dive into what is Icechunk, introduction to Icechunk. So first of all, why do we need Icechunk? What's the motivation for creating this new file format? There are a lot of archival array-based file formats out there like HDF, NetCDF, and GRIB. And this is where most of our existing data in weather, climate, and geospatial is produced. However, that data is not, those data formats aren't really designed to work well in the cloud. And so they can be slow, and we can't get that sort of cloud native performance from those file formats. And of course, we're still producing so much data in those existing file formats. There's been a real trend in our community to start adopting Czar as a new cloud native format for multidimensional array data. But Czar has some limitations. First of all, data have to be transformed from those archival formats into Czar, which can be an expensive proposition. Czar is not safe to use in an operational context where you have multiple readers and writers accessing the same data at the same time, so it has some concurrency issues. And finally, when you're using Czar in this way, it can be hard to detect and fix corrupted data, rollback problems, etc. So all of these challenges mean that our community hasn't really been able to take full advantage of this sort of transformative potential of the cloud and fully adopt a cloud-based approach to storing and managing scientific data. And so this is why we decided to create Icechunk. So Icechunk is a brand new project launched last fall, which we characterize as an open source cloud native transactional tensor storage engine. So just a little bit about Icechunk. If you want to learn more about Icechunk, you can go to icechunk.io, the website. You can go check out Icechunk on GitHub, earthmover/Icechunk. If you're over there, please give us another GitHub star. So Icechunk, as I mentioned, is a transactional cloud native storage engine that works together with the Zar library to create a full user experience around storing, querying, and updating multi-dimensional array data in the cloud. So it's designed from the ground up to work with cloud object storage and supports all major cloud platforms, S3, Google Cloud Storage, and Azure. It is highly interoperable with the rest of the ecosystem, in particular Xarray and virtualized Zar. However, it's not written in Python for the most part. It is a Rust library with a thin Python wrapper, and that's part of the reason behind some of the great performance that we've seen from Icechunk. It can also be used from Rust, and there's Julia support in the works. And Icechunk is 100% open source, licensed under Apache 2.0. So if you take nothing else from this webinar, just go check out Icechunk and give it a try. It's really cool. We're super excited about it. So what is a transactional cloud native storage engine for Zar? I'm going to quickly review this. If you use Zar today, Zar is a library that stores multidimensional arrays in the cloud. It just stores multidimensional arrays, period, whether on file system, in memory, or in any number of storage devices. If you're using Zar in the cloud, you're using it together with the FSSpec library, something like S3FS or GCSFS. And FSSpec manages the I/O, sending data to and from the cloud object storage. And it does so in a pretty lightweight way. Zar just represents data using keys and values, so it can store anything in a key value store. And FSSpec just passes those keys and values through unchanged. With Icechunk, we replace that FSSpec layer with Icechunk. And not only does Icechunk manage that communication with the cloud object store, it also has its own schema for storing data. And that schema enables some really powerful features, some of which I'll describe today. So by operating at the store level, Icechunk augments Zar with a bunch of powerful database-like features. So just to review what Zar is and what I say when I mean Zar and the Zar data model, here's an outline of what type of data can be stored in Zar. So Zar ultimately manages data within groups and arrays. Those are the two core entities within a Zar store. And this is the same as the HDF5 data model, by the way. So we're representing data as multidimensional arrays with one or more dimensions. Then physically for storage, those arrays are split into chunks. And those chunks are much smaller arrays that are the individual unit of compression and storage. All of these types of entities can have metadata attached to them. And this structure is a really broad, powerful data model for scientific data. It can be used for geospatial data. It can be used for simulation data. It can be used for microscopy data. This is why Zar and HDF are used so widely across the scientific and technical data ecosystem. So the entity that we've got in Icechunk is what we call a repo, which is, you can think of as one of these Zar stores. It can have a hierarchy of multiple arrays and groups. But Icechunk also introduces this concept of a time evolution and history to how the data evolve over time. So each state of this Icechunk repo is represented by what we call a snapshot. And every change that we make to the data is sort of sealed with a new snapshot. And when folks come to read the data, they're only ever going to see one of these committed snapshots rather than potentially seeing data in some intermediate state. So this is really important because it makes Icechunk function a lot more like a database. And so this is why we at Earthmover are putting Icechunk at the core of the data platform that we are building. So here is a description of the broader architecture of the Earthmover platform. And what you can see is Icechunk is really the core library that is responsible for managing communication with object storage, reading and writing data, and creating transactional updates. And it can then be used in a variety of ways. Data scientists can access that data directly from object storage and integrate it with Python and other machine learning tools. Or it can be used as a backend database for various services. And so we have a layer in our platform that serves up map tiles or OpenDAP endpoints or environmental data retrieval protocol, all using Icechunk as the backend for those services, thereby providing a scalable, performant, cloud-native backend for those APIs. So there's a lot of reasons to love Icechunk as a user. I've talked about ACID transactions. Icechunk has incredible speed and performance compared to the vanilla Python stack. There's this ability to virtualize over existing netcdf, HDF, and GRIB files. And then finally, there's data version control. I'll just give you one little sneak preview at the speed and performance. So here's a project that we're currently working on with NASA, where we are working with NASA to improve the speed at which time series can be extracted from all of those petabytes of netcdf files that NASA is storing in the cloud. And so here the task is to extract a 1-month time series from half-hourly precipitation data, where each half hour is stored as a separate netcdf file. This means scanning over close to 1,500 netcdf files. And so the baseline service that they are using to do this takes 45 seconds to perform that sort of scan. And with Icechunk, we're able to extract the same time series in just 3 seconds. And this is largely thanks to the extremely efficient I/O stack within the Icechunk library. However, none of that is really the focus for today. We are really focused here on this topic of data version control. And so this ends the general introduction to Icechunk, and now we'll focus in on version control and how we do version control with Icechunk. Okay, so I'm going to assume that most of us are familiar with the concept of version control for code. Using version control for code is really an industry standard. Most of us who develop software wouldn't really dream of trying to do it without version control, something like Git. So just to sort of review the obvious here, Git and similar version control systems are based on tracking diffs between text files, right? So we'll have a directory of code files, and we'll make some changes, and then we'll do git commit, and we'll create this new snapshot of the state of that data. Version control systems also offer the idea of branches, which are sort of moving pointers to one of those commits, and also tags, which are immutable pointers to one of those commits. So working with code this way really enables fast yet safe evolution of a shared code base with multiple people potentially working on the same code, the need to merge changes and reconcile differences between different committers to that code. And it also offers verification of the contents of the repository based on some hashing of the data. So this is version control for code, and I'm assuming most folks are pretty familiar with that. Now, if you might ask yourself, well, let's just use Git for our data too, so we can track all the changes to our data. the same way we track changes to our code. That sounds useful. Git, though, is not optimized for text files. It's not optimized for binary files. It is optimized for text files. It really does not handle large files well, period, and particular large binary files. These are, core limitations in the design of Git. There are some solutions out there for version control on data. So here is a review of some of those existing options that people have today. So over on the left, we have two sort of Git extensions, if you like, that enable you to work with large binary data. There's Git large file storage, and there's DVC, or data version control. Those leverage Git and extend it in various ways to allow you to also have some files stored remotely on a remote server. Both of those assume that what you want to do is clone that repository from a remote location to a local disk and bring down all those files locally. Over more on the cloud native side, we have LakeFS, which offers Git-style branching with a generic S3 compatible API. Very cool platform. Does require operating a special server and proxy for the S3 underlying S3 object storage. And moreover, all of these solutions are still fundamentally file-based. They don't quite understand data structures. They don't know arrays from tables, from images. It's all just blobs or files, right? And so there's some missed opportunity there to offer a more nuanced version control experience that's tuned to a specific data model. So more generally, at Earthmover, we really believe that files and asking data scientists to spend a lot of time thinking about files is a thing of the past. And we really want to move into a future where we're interacting with data in a more database style fashion, looking at the entirety of a data set, pulling data on demand from the cloud without having to explicitly think about managing files, uploading, downloading, etc. So we're looking to deliver a file-free data version control experience with Icechunk. So let me explain how it works. Now, I mentioned that the key property of Icechunk is that it introduces this idea of these snapshots of the state of your Icechunk repository at a particular point in time. And this is really the core of it. That's all you really need to understand. Icechunk has the ability to create an immutable identifier, some ID, that says this is the exact state of this repo at this particular time, and that will never change. Maybe it could be deleted or cleaned up, but if you open that state, you'll always see the same data. Just like if you open a Git repository and check out a specific Git commit hash, you'll always go to the same state of the code. And so Icechunk, similar to Git, allows efficient incremental storage of updates. So this is the sort of data model: arrays, groups, metadata, chunks. In Icechunk, the sort of minimum unit of update is a single chunk. So if you want to write some data, overwrite some data, you're only going to store the minimum number of chunks necessary to represent the latest state of the data. You don't have to copy large volumes of data in order to have multiple versions. As I'll explain on the next slide, Icechunk supports also branches and tags, just like Git. Icechunk provides fine-grained tracking of semantically relevant changes to the data. In other words, it knows what you did to your data in terms of this data model. And that's a big contrast from something like Git LFS or data version control or LakeFS, where all it can tell you is, oh, you changed a specific file. Whereas Icechunk can tell you, oh, you extended this array in this specific way, or you added metadata to this group. Icechunk is fundamentally cloud native and doesn't require you to clone or copy the data to a local file system in order to work with it. You can interact with these data sets, create versions, update things, just purely talking to cloud object storage. And then finally, to deal with the potential growth of data in storage, as you create more and more versions, Icechunk offers some sophisticated capabilities to expire and garbage collect unwanted versions of your data to free up storage space. So I'm going to walk through all of these things in my demo. First, I'm just going to give you a little bit more detail about what we're going to see in the demo. So a really important concept in Icechunk is the snapshot. We're going to see a lot of these little IDs, and these represent specific states of a data set. And you can think of our snapshot history as a tree where each snapshot points at its parent snapshot and on all the way up to the initialization of the repository. Now, within this context, we can use both branches and tags to give a more refined user experience. So a branch is just a pointer, a name such as main, that points to one of these specific snapshots. A tag is another pointer to a snapshot, but with the distinction that a tag is immutable. So once we make a tag, it's always going to point to only one specific snapshot. And if we delete it, we can never create it again. And so tags are very useful for publishing and putting out a very specific, well-known version of a data set. Branches, on the other hand, can allow us to evolve. So one really cool thing we can do in Icechunk that I'll demonstrate in the demo is that we can create a development branch where we can stage changes to our data, work on things there, do some quality control, do some checks, and then only once we're ready, update the main branch to point at that new version of the data. Just like we commonly do with sort of production code. We've got dev, staging, prod. That sort of workflow is possible. So finally, what is this all for? Who cares? What's the point of data version control? Well, there's two pretty specific use cases that we have in mind when creating this capability. The first one is the sort of data publication and reproducible science scenario. We're seeing a growing number of data providers who want to provide access to czar data in the cloud as their main way of sharing data with their stakeholders, whether those are the public, some private stakeholders, or potentially even a paying customer for that data. And that data producer is constantly updating that data in storage. This creates a challenge, though, for the data consumer who's consuming that data, because they may not know exactly what state the data is in when they're accessing it. So for the purposes of reproducibility, we'd like to be able to run some sort of code against that data set that will always produce the same result, regardless of what other future updates may come through. And so Icechunk enables this by creating these immutable references, snapshots, tags, pointing to a specific state of the data set, which you could then point to, potentially even cite, and use as part of a reproducible scientific analysis pipeline. The other related use case is for machine learning workflows. So machine learning involves a lot of iteration between data and model. If you're trying to develop a machine learning model, you're engineering on both the input features that you want to feed into that model, as well as the model architecture. And in general, you only want to be changing one of those things at a time. And so Icechunk allows you to have really tight versioning of your training data for a machine learning workflow, so that when you go to train the model, you're always pointing at the same state of the data, even as you may continue to evolve that data and into a new state. Another really cool use case that we've discovered in working on this demo is you can even store your model weights in Icechunk, potentially in the same repo alongside the training data. And I think this is a really cool unlock, because what are those model weights from say a neural network? Well, they're just tensors, and so they fit perfectly in Icechunk. And time permitting, we'll get to look at a workflow like that. This brings me to the end of my slides. And so I'm now going to stop sharing this, and I'm going to go into a Jupyter notebook where I'm going to share some live code with you. I'm going to do this cautiously, knowing that it's very hard to follow along when someone is just running a bunch of code cells on the screen. I was tempted to live code this whole demo. That's what I used to do when I was teaching environmental data science. But I think it will move a little too slow. I don't think folks here are interested in following along with this line by line on your own computer, although you absolutely feel free to. Instead, I think folks want to get a broader view of what this can do. So I'm going to run through this notebook, executing these cells live. And please stop me if something is not clear, if you want to pause, if you want to double click on something, I'm happy to do it. So without further ado, let's dive into the demo. I am going to start running this notebook. And I'm just going to start by doing my basic imports, NumPy, Zar, and Icechunk. I like to import Icechunk as IC. Well, what we're going to do here is create a new Icechunk repo or repository. There's a slight chance this won't work if I forgot to delete the thing that was here first, but I think I was prepared. Great, it worked. So we've now created a new Icechunk repo within this S3 bucket at this prefix. After the webinar, I'll share all this stuff so you can go explore it on your own. So the repo has nothing in it. And what I'm going to do next is I'm going to write some data to this store. And so here's the syntax we use for doing this. And if you were at our last webinar, you'll notice the API has changed a little bit. I think we've made big improvements to the Icechunk API, how you actually read and write data. Here's what we do. First, in order to write any data, we need to create a session. This is a context that is pointing at a specific snapshot, which we can then use to evolve to the next snapshot. And here, this is the name of the branch that we want to create the session on. And notice we specified this is a writable session. So that means we can make updates to the data in this session. Now, attached to this session is a store, a valid Zar store that we can open up, read data from, and write data to. So we're going to create a Zar group. We're going to set some attributes on it. We're going to create an array, and then we're going to write some data to that array. So this array has 10 million elements in chunks of 1 million. Now, if I say session status, Icechunk knows what changes I've made to my data. It sees I created a group, I created an array, I updated some attributes on the group and the array, and I have written 10 chunks. Now I'm going to complete that by calling commit. And this creates a new snapshot and gives me back a snapshot ID for my data set. So this is created, if you like, a first version of this data. Now what I'm going to do is make some changes to this data set. I am going to modify it. We can't reuse the old objects we created with the old array, the old store, because that session has been committed and it's no longer valid. So we have to create a new session here and open up the array that we want to interact with. Here we can see it's the array we recently committed. And I'm going to append 2 million random elements to it. You can see here, we added 2 chunks to the data set. Now, let me tell you one of the things that I love most about working with Icechunk. It's impossible to screw up your data. I don't know if you've ever had this feeling as a Zar user of accidentally overwriting something, making a mistake on the data, and you get that sinking feeling in your stomach where, oh no, I've screwed up something and I can never get it back. I've certainly been there. That's part of why we created this. With Icechunk, you can always just discard any changes within your current session. Everything is undoable. Nothing is ever overwritten permanently. And so that's what I just did. I discarded changes and I say, phew, okay, I actually meant to append 3 million elements. So let's do that. We get an update on the status, and now we can make a commit. And at this point, we can look at the ancestry of this data set. And we can see it's a bit hard to read given how zoomed in my screen is here, but we see 3 snapshots going backwards in time at different times with these different messages. So repository initialized, wrote in, initial data, and then appended data. So this repo now has 3 snapshots. Next, I'm going to showcase how we use tags and branches. So what I'm going to do here is I'm going to create a tag referencing that first commit that we made to the repo. In this cell, I'm going to create a branch called dev, and I'm going to base this at the current main branch. This is maybe a difference with Git. There's no state to the repo in terms of which branch you're on or anything like that. That only exists within a session. So when you're creating a branch, you're creating a tag, you need to explicitly tell Icechunk which snapshot you want to point to. Now that we've done that, we can list the branches that are present in the repo. We can list the tags. And we can even look at diffs. So here we've got a diff from version 1.0 to main. We can see we've made some changes to the array between those 2 snapshots. We can also get the specific commit ID of any one of these branches, and here we can verify that main and dev are both at this point pointing to the same snapshot. So now what I'm going to do is I'm going to make some changes on the dev branch only. So here I'm going to make a new writable session on the dev branch. I'm going to open up my array, and I'm going to overwrite the last 5 million elements of the array. And we can see that creates an update to 5 different chunks, and I'll commit those. And so at this point, we've got a couple different states of the data that we can refer to. Here, we're going to look at the state of the main branch, and I'll just look at the last element of the array. Here, we'll look at the 1.0 tag. We'll look at the last element of that array. And here, we'll look at the dev branch, and we'll look at the last element of the array. And those are all different values in all of these different scenarios. Finally, to sort of wrap up this part of the flow, we made some changes in dev. We decided everything's good. Great. Let's bring our main branch up to date. So we'll reset the main branch to the status of the dev branch. So these are all the sort of operations that we would do with Git on code, except here we're doing it with data, specifically multi-dimensional array data. So that's sort of part 1 of the demo here. I think it's a little dry, but hopefully it really communicates the power of these features, the flexibility of this model. In this next part, I'm going to go a little deeper and showcase some of the most powerful components of Icechunk around detecting conflicts. If you've ever used Git, you know that Git has a very sophisticated mechanism for preventing you from accidentally creating conflicts or invalid updates to your code. And Icechunk does the same for your data while trying to help you merge and reconcile changes that come from different places. And so to do this conflict detection, we now have to simulate multiple different users who are interacting with the data at the same time. And this can be a little bit mind-bending because as individual users, we only generally have one session going at the same time. However, what we've learned is there's a lot of scenarios when folks want to have multiple processes that are talking to the same ZAR data at the same time. And that's when you can get into all kinds of consistency nightmares without Icechunk there to help you. And so here, the scenario we're going to model is 2 different users who are trying to modify the same data at the same time, Sounds like a nightmare, right? But actually, it's totally fine in Icechunk, and you can absolutely, do this in a safe way. So here, session A is going to represent one user, and session B is going to represent the other user. And so we're going to create one session for A and open up the array, and one session for B, open up the same array, and we're going to make two mutually incompatible writes. We're going to make two different writes that are not to the same location within the array. So array A is writing to the first value of that array, and B is writing to the final value of that array. And if I would just do, for example, session A status, I'll see we updated chunk 0, and session B status, we updated chunk 14. So in principle, there's no conflict between these. So I'll start by committing session A, and that's going to work. A got there first. That commit goes in. Now I'm going to try and commit session B, and here we get an error. So by default, Icechunk will never commit a session if another commit came in and there's a new, more recent snapshot than the one that session thought it was pointing to, right? And so it said, failed to commit, expected this parent, and got this actual parent. So for this branch. And so here we can see that's the commit that just came in. So it says, no, whatever happened, your current state of this session is now out of date. So your update is invalid. Now, to get around this, we have an option to rebase our session. So rebase may be familiar to you from Git. And the way rebase works is basically rewrites the history of this current session that we're in. And we're just going to use a option here when calling rebase to detect if there's any conflicts at all between those two branches. And if there's no conflicts, no error is going to be raised and our commit will go through. And that's exactly what happens. And so now when I look at my repo ancestry, I can see that in fact both of those commits went in, first A and first B, and the state of our data is totally consistent, no conflicts. We were just very careful. For the next example, we're going to do some updates that do have conflicts. Okay, so it's very similar. We're going to have two concurrent sessions on the same repo, except they're both going to update the exact same data element. And in fact, this is really what matters here is that they're trying to write to the same chunk. The chunk is the minimum unit of conflict detection currently in Icechunk. We don't have the ability to parse a conflict within a specific chunk. We just know this chunk has been overwritten or not. And so I'm going to try both of those commits, and again, we'll get a failure for session B. And if I try the same conflict, same rebase strategy that I tried before, I will get a rebase failed error, and it'll tell us the chunk double update for a specific array. So these two different histories have both tried to write to the same chunk. And so at this point, we have several options. We could retry the whole operation, reread the data, and seamlessly merge our changes with that original data. Or we could use this strategy. On chunk conflict, use our changes instead. So just overwrite whatever B did with A. That, by the way, is the default behavior of ZAR without Icechunk in the way. You'll just clobber any changes that another session might have happened to make in this scenario. However, Icechunk allows you to do this in a hyper-controlled, careful way, detecting exactly what's happening along the way. And then now if I open that array and I look at the value that I get there, indeed, I get the value that I was expecting from B. Okay, so as a final step here, we're going to clean up this repo. So along the way, creating these different branches and tags, and overwriting data and making a lot of commits, I generated a lot of extra data. And maybe I don't want to keep that data around forever. Certainly, if I wrote the whole repo many times over, I'd multiply the amount of data stored. And so I'm going to start by deleting both that dev branch and deleting the tag. I don't care about those states anymore. I'm going to look at the ancestry of my repo and see I've got, I think, 8 commits here. I'm going to look at when was the latest snapshot written, just a few seconds ago. And then I'm going to call this function called expire snapshots relative to this time. So what that's going to do, it's going to take all those snapshots that were written before that time, that are not pointed to by either a branch or a tag, and it's going to rewrite the history so that they're no longer part of the repo history. So now if I look at ancestry, I see there's only 2 snapshots left, the very first one and the latest one. Note the data at that state is still all there. We just can't return to those previous versions. And then finally, no data have been deleted yet. The data are all still there. I'm going to run a separate operation called garbage collection, which is going to actually go and delete the data files that we don't need anymore. So we see we deleted 6 snapshot files and 6 chunks, which has freed up some data on our storage. Just to wrap this up, we'll go look at what's actually in storage. Let me zoom out a little bit. There we go. And we can see this is what's in this repo. We can see we've got our branch, we've got a chunk manifest and some chunks, some snapshots, and some transaction logs. And so this is a clean Icechunk repository with all of the unnecessary state cleaned up and deleted. So this is the end of the sort of technical part of the demo. What I'm going to do now is just give you a really quick tour of a much more sophisticated use case for this that I had a lot of fun putting together. And that is going to be to create some test data for a neural network classifier model. And so I'm not going to try to explain this in as much detail, but hopefully it'll give you a flavor for what Icechunk can do here. So I'm going to create a new repository and create a root group in it. And what I'm going to do is I'm going to run a little turbulence model to generate some data. So this is going back to my days as a physical oceanographer. We're actually running a little ocean simulation of a little patch of turbulence in the middle of the ocean. And what this does is it produces a data set that looks kind of like this. Just some swirly potential vorticity field represented as a 64 by 64 array. What I'm going to do is run this model and write the data to an Icechunk repo as the model is going along. And so I'm just going to run a few more cells and make that happen. The way that I'm doing this here is I've created a queue and running the Icechunk process on a separate thread. I'm running this model in a loop, and every snapshot, I'm sending a piece of data to this thread, and we have a separate worker process that's storing it to the Icechunk store. And then when all of that's done, we're going to commit those changes. The cool thing we can do is we can keep appending to this as much as we want. So if I want to run another one here, I can do that. And then I can go run another model with different parameters and put it in a different part of this Icechunk repo in another notebook. So that is a lot of fun. This allows us to sort of concurrently generate data for our machine learning training workflow. And so what we're doing now is essentially building out features that we're going to use to train a model in the next notebook. So we can see both A and B ran. We'll have a look at what we've created here. If I open this up, I can see I've got 401 snapshots of this variable over in this notebook of a certain parameter set. I'm going to run this one more time to generate another set of training data over in B. And then, what this is doing for us is it's creating an example of a sort of data set that we then want to use these versions for in another workflow. So we'll let this one quickly finish itself, and then we'll just say repo ancestry. You can see, we'll have to put in branch equals main here. So we can see we've gotten about a half dozen commits. Now we can go over to run a machine learning workflow on top of this data. So here I'm going to open up that same data. I can see, sorry, I want to change it to this one. Open up that same data. We now have two different data sets from these two different models. This is what the data looks like. And we're going to try and train a machine learning classifier to tell the difference between these two different simulations. I can't really tell any difference by eye by looking at these, but we'll see the model is actually able to pick it up. So here we're just going to define a really simple convolutional neural network-based model binary classifier to tell these two models apart. We'll load the data from Icechunk. We'll normalize it, and we'll run a training loop where we're trying to minimize this objective. And you can see after a couple epochs, it does kind of well. The model has trained up, and just to sort of put a bow on it, we can actually store our model weights themselves to the Icechunk repo. So we're going to take in the same repo, we're going to pull out all the neural network weights from PyTorch, and we're going to write them in the same repo alongside our training data. We're going to add all of these weights and commit that to our Icechunk repo. So I think this is a pretty cool way of using these things together. We know that this snapshot model weights were trained on precisely the data from the preceding snapshot, allowing us to have a lot of reproducibility and clarity into exactly how our model was trained and where the data came from. So I know that last one was a bit of a whirlwind, but I wanted to show something other than just some toy dummy data, and so there it is. I will stop presenting now, and I would love to spend the last 10 minutes with any questions or comments folks have. Alana, do we have a system to do that? Yeah, just raise hands. That sounds great. I see someone with a hand up, but how can I see who has their hand up? Just speak up. Are you allowed to unmute?
Maybe just put it in the chat.
I would love to have someone actually say something other than just me. So I saw someone had a hand up. Where is that happening? Ah, Daniel. Okay, go ahead. Go ahead, Daniel.
Okay, cool. Yeah, nice. This is working. Yeah, so I mean, this is looking absolutely amazing, of course. And my question is, if I'm writing in a session and my job fails midway, what can I, and say I've written, I don't know, gigabytes of data and that may have failed, what can I recover? Can I recover that session? Has that data been written on the object? Or, yeah, what can I do in that case?
Well, I'll tell you the answer now, and then I'll tell you what's possible. So I believe the answer is now. If you lose your session, your data have been written to object storage, but there's no way to recover the session. And so you have the worst of both worlds. You have extra data, but you can't access it, so you're out of luck. That data would be garbage collected if you run garbage collection, because there wouldn't be any reference to it. I believe we should have a way to enable you to, well, I don't know. Seba, can you answer this question that Daniel is asking? What happens if you lose your session? What happens to the data that was in it?
We have several ideas that we are thinking about, definitely something that we will want to take care on. The main thing that you could do today is kind of do fake snapshots, right? You can make a smaller task in which you keep committing, right? And instead of doing your huge task over gigabytes of data, you can continue commit in 10 pieces, so you only lose the last one of them. So that would be something kind of manual that you can do today. Then like, what we want to do basically is do that kind of automatically. So we can store like checkpoint your session and then recover from that last checkpoint. And like Icechunk is very well suited for that kind of thing because we have all the concepts we need to do it. Like we have a chain set and we can serialize it, and we have a transaction log and all that. So I imagine that soon something like that is gonna appear as a new feature in the changelog. Yeah.
Okay, cool. I see a question in. I would love for folks to come off camera and speak up if you're feeling like it. But I see someone asked a question. There is a Q&A app that you can use. So Anonymous asked, is Icechunk only necessary if using data in the cloud, or does it make sense to use when loading local data? I think you can absolutely use this locally in just file system storage if you want these sort of data versioning features in a local state. Yeah, while cloud usage is definitely one of the main design factors in Icechunk, it's absolutely not necessary to use. And just like you can use Git by yourself on your own local files, you can use Icechunk the same way. Okay. Couple questions in the chat. Eve asks, here's an example. Org has a bunch of NWP models with several model runs, each having several forecast hours. Currently, each model run has a file name. Would it make sense to create a single ZAR file endpoint for NWP product number 1 and keep appending model runs forever? Would it be easy to extract a specific forecast time, which means different forecast hours in different model runs? Yes, this is exactly the structure of data that we use in Earthmover. This is how we organize, for example, GFS data within our platform. And so you can see how we do that for a single model in the link that I just dropped in the chat. I do like just appending each forecast to a single array, a single data set. That way you can easily query either across forecast time or lead time. It's very flexible. I would not put different models in the same repo. In general, you want to put things in the same repo that need to be updated through a transaction because the data is coming in from the same source at the same time. And so I think an anti-pattern with Icechunk is to have like just one big Icechunk repo, and an organization puts all of its data into one repo. That's probably not the best pattern because there is, of course, an overhead to reconciling those different changes from unrelated data sets. And ultimately, you don't need those protections. But yes, it's a very common use case. And thank you for asking it. Okay, Ben asks, I'd love to hear about how this would work with virtual data sets based on source data in HDF5, TIFF, or some other format. Yeah, so everything I showed works with virtual data as well. The difference being, rather than writing new chunk data to the object store, you're just creating references to other HDF or NetCDF files that are already up in the object store somewhere else. And so you could have the same versioning, all of the same features, branches, tags, version control, but referencing files that are not contained within the repo. It's kind of a deep topic, and it probably merits its own webinar, but yeah, happy to answer a follow-up question.
Yeah, so let's say you wanted to change some of the values that correspond to just one chunk of data. Would you be like, would that then write that one chunk and then for all of the other chunks refer to the original source data?
Yes, correct. You can incrementally change just one chunk at a time and replace it, overlay a native chunk. And that's completely invisible to the user of the data. Furthermore, you could tweak the metadata as well. Right, yeah. So you could change the metadata, augment the metadata while still referencing the same underlying HDF files. It's super cool.
So you mentioned storing the source data in some other place and then just like referencing it as like an S3 bucket or a URL or something somewhere else.
Yeah.
But like one of the challenges with this virtualization approach is you need to be extra sure that the source data is persistent. Otherwise, this whole approach kind of goes out the window.
Correct.
So do you have ways of managing those source files internally within Icechunk, or are we expected to come up with our own kind of persistent data storage solution for that?
I don't quite understand what you're getting at.
So if I stored an HDF5 file at a certain location and then I updated that HDF5 file, but it's in a separate system and all Icechunk has is a URL to that data, it won't know that it was updated, right? And so then it'll
it
just
will
kind of,
though, because it's not all it has is a URL. It also has a e tag for that file and a last modification date. So if it detects that either of those things has changed, it will raise an error and say that your reference is no longer valid. Of course, it cannot manage. It cannot. That is out of its control. And I think this is an irreducible feature of this approach to virtualization. If someone goes and deletes the files you're referencing, of course it's going to break. You know, I think of it as like a symlink, right? In Unix, like if you make a soft link to a file and then you delete that file, well, your soft link's going to break, and that's the price you pay. And if you really wanted to have that data purely under your control, don't use the virtual files. Just write it natively to Icechunk, and then everything is self-contained within that repo.
Yeah, totally. I was thinking about an alternative solution, which would be that Icechunk would manage like a separate store for virtual files, and if there are any references to those files, it would like protect. It would protect versions of those source files so that you could always have links to like a persistent state of the source files.
Yeah, that's interesting. You know, you should open an issue for that in the Icechunk repo, and we can discuss it some more. I think it's an interesting concept. Let's see. I think we touched on virtualization. The last question I think we have time for is from Gerald. How well does this work with highly concurrent writes across multiple hosts, but where there are no conflicts at the chunk level? So Gerald, it works great. There's two different ways you can do what you're asking for. You can do what's called a cooperative session, where all of those different hosts are coordinating as part of one single session and commit all their changes as part of one transaction. Or you can have them also be uncoordinated writes that are writing, you know, without any coordination and then trying to commit, in which case you have to do a bit of a retry loop on the commit. But if there's truly no conflicts, that all resolves and goes through, and we have that sort of workflow running today. Go ahead, Seba.
One minor comment, like there is no coordination between the writers inside Icechunk, so there is no overhead. You will write at the full speed of each writer, and we only do kind of in an optimistically locking way. And then at the end, when we commit, we're going to detect conflicts and all that Ryan showed.
All right, folks. Well, this was a lot of fun. Hopefully, answer some of your questions, gave you a taste for Icechunk. We're very close to the Icechunk 1.0 release, so we're looking forward to getting this out there into people's hands. Of course, you can use it today already, but it's about to become a lot more stable. And so, yeah, it was really great having so many folks here, and feel free to follow up on GitHub with any more questions.